Okay, we will focus only on uniform circular motion. Uniform means it's going to be at a constant speed. Circular means it's circular, so it's around a circle. Now, can I say, look here, you see you have a point, it goes from here, there, and it's going around at the same speed. Okay, so it has a number of revolutions per second. Can I say that the velocity is constant? Remember, velocity is a vector, right? Do you see that the velocity stays the same? Is the vector staying the same? The magnitude, yes. What about the direction? No, it changes, right? So as long as either the magnitude or the direction or both changes, that means you need to apply a force. And this force is called the centripetal force. So last time I show you like a video, but if there is no force applied, off tangent it's gonna go. Okay, it wants to keep going in a straight line at a constant speed. No, you can't. There's a force pulling in, right? So the best example will be if I have yeah, if I have I used to have, I don't have anymore. Okay, huh. It's okay, but let's see if I have a picture. So here, you see, if you want to maintain that circular motion, you need to apply a force, right? And the force is toward the center. So that's why it's called a centripetal force, right? We talked about that last time. And let's see if I have a like a simulation. So typical conceptual equation, let's see, circular motion. You see, let's forget about gravity. You see, it's a circular motion, it's uniform. And if I cut the string, if I let go, you see how it goes? It's gonna be along a straight line at a constant velocity. So typical conceptual equation for the MCAT, for example, they want you to say that it's gonna go this way. It does not. It wants to keep the same velocity it had before. Is that clear? So typical conceptual equation. If I'm going to try to hit the target. Boom. You see that? So the velocity is always tangent to the trajectory. It's always tangent. So this is called tangent, right? And if there is no force acting on the object, it wants to keep going along a straight line at a constant speed. Okay, so that's a review from last time. Likewise, if you take, for example, the moon, right, or the sun, and let's say we take the sun for a change. So this is the sun, and supposed to be nice and spherical. And you have the earth. So this is the earth, right? So the earth wants to go, has a velocity here. So it has a velocity. It wants to keep going in a straight line at a constant speed. What's going to happen? The sun is pulling, right? So no, you can't, right? You can't. Why is it that you can't? Because there is a centripetal force, right? And what is that centripetal force? Is because of gravity, right? So you see that in that case, the Earth is about moving at a constant speed. Okay, it takes about 365 days to go around. Okay, and you see that force is always perpendicular to the velocity. When the force is perpendicular to a velocity, it cannot change the speed, okay? Because it doesn't pull on it, right? It doesn't make it go slower. It doesn't make it go faster. It just changes direction. Okay, so again, I want to keep going in a straight line at a constant speed. No, you can't. Right? So that's how it works. That force here is called the centripetal force. And if you connect all the dots, you're going to get a circular motion. Is that clear? The time it takes to go around when the motion is uniform is called the period. Okay? Okay, the period. So the period usually is in seconds. That will be the time it takes to go once around. Do you agree? And how can we compute the distance around the circle? What's the distance around the circle? So diameter will be twice the radius. If you go around once, it's called the circumference. And the distance around equals what the circumference equals to? Hello? 2 pi. 2 pi r. Okay, so the distance around the circle equals 2 pi r. So if you take a string, you go around a perfect circle, the distance will be 2 times pi times r. The distance here is in meters, the radius is in meters. This is a scalar. Remember, distance is a scalar. That was a question in the test. Distance is a scalar, right? So the speed, if you have a uniform motion, so it's moving at a constant speed, so the speed is distance over time, which is 2 pi r, okay, for example, over the time elapsed, which we call the period because it always takes the same time to go around. Is that clear? So it's not that hard. Okay, so this is called uniform circular motion. And again, if there is no force acting, okay, off tangent it goes. So here you see that the velocity always keeps the same magnitude, but the direction keeps changing. If the direction keeps changing, that means there is a change in velocity. Okay, not the magnitude. Magnitude stays the same, but the direction keeps changing. Is that clear? Mm-hmm. You see, it doesn't point toward the same, in the same direction, so the velocity is going to change. Is that clear? Yeah. Okay. So what do you think? Which one is false? Hello, hello. Wake up. Which one is false? Okay. A? Yes. The velocity of the object is not constant. The magnitude of the acceleration is constant because the force is constant. Okay, the acceleration is toward the center? Yes, because the force is toward the center. Remember what I taught you the first lectures? Acceleration and force, it's kind of the same thing. They are proportional to each other. Acceleration is just the force per unit mass. So if the force is the same, acceleration is the same. The magnitude of the velocity is constant? Yes, the magnitude of the velocity is the speed, so it stays the same. The velocity is tangent. Yes, that's true. You see, velocity is always tangent to the path. Is that clear? Mm-hmm. Okay. When we say uniform circular motion, what does uniform means? Constant. Constant one. Constant speed. Very good. The speed is constant, not the velocity. So they try to trick you sometimes. They say, it's a constant velocity. No. It's just a constant speed because the direction keeps changing. Okay? So remember the polar graph? I asked you to point it out. If you look at your polar graph, if you go once around, okay, that will be 2 pi in radians or 360 degrees or 1 revolution. So if you go half of a circle, that will be pi or 180 degrees, right? Okay, so let's write this down. So if you go once around, by the way, if you come back to the same place, displacement is 0. But anyway, that's not the point. Okay, if you go once around, that will be 1 revolution. 1 revolution is the same thing as 2 pi. Okay, that's 2 pi. That will be in radians, which is the same thing as 360 degrees. Do you agree? Okay, and the distance once around equals 2 pi r. So you can always do proportion. Okay, so for example, if I say 8 revolution, what's going to be the distance? So you go once, twice, 3, 4, 5, 6, 7, 8. So it's like you take a string, you go once and twice and 3 and 4 and 5 and 6, 7, 8, right? How can I find the distance? I can say 1 revolution is 2 pi r. Okay, the unit here is in meters. So you cross, multiply, divide, get x. Is that clear? So with all of that, you can do proportions. So for example, I can say 2 pi is 360. Okay, so if I have 180, you divide by 2. So divide by 2, you're going to get 2 pi divided by 2 is going to be pi. Very good, right? If you divide by 2 here, you're going to have pi over 2. So that's going to be 90 degrees. Okay, and you divide by 2, you get 45 degrees, which is pi over 4. Got that? Okay. ABC, 1 revolution is 2 pi in radians. That will be degrees. That will be in distance, 2 pi r. 1 distance around. Okay. Okay, so let's try to do this one. Did we do this one?
No.
Okay, so let's try to do this one. You have different ways to do it. You can talk to each other, help each other out. First of all, you need to draw. Okay, you cannot survive physics. You cannot survive physics unless you draw. And you are very lucky. Most of you have a tablet. So with the tablet, you can draw and you can erase. At my time, when I was your age, I had like an eraser that, you know, those little square thing eraser and a pencil. That's what I had. Okay. You're doing it? Don't stare. I see people staring. So east, north, south, west. So you have to draw, right? I'm going to make a dot instead of an airplane, and it's going west. East, you're right. East. And then it's making a turn Okay, it's like it wants to turn. It's a circle. It's supposed to be a circle. And now it wants to go south. So it's only going through this path here. So it goes from here to here. So by the way, that problem comes from your book, Johnson and Cotnell. So it's doing how much of a circle? 1/4, right? It's like when you were in middle school, the pizza thing. It's 1/4 of a pizza. Okay? So you have different way to do it. Do it. Help each other. That's the radius here. So you have different ways to do it, but the speed is always the distance divided by the time. And that time here takes 15 seconds. So you have different ways to do it. If you want to find the time it takes to go once around, how much is that going to be? 15 seconds to go 1/4, 15 seconds to go half, 15 seconds to go 3/4, 15 seconds to go a full circle. So how much is that altogether? 60, right? Do you say 60? 60. So the time it takes to go around is going to be 60. Do you agree? So you can say the speed is, I'm going to say the distance to go around, right? So once around, that's going to be 2 pi r over 60. You don't have to do it this way. You can also do pi over 2 times r, right? And you divide by the time. Otherwise, you can stick to the equation. The time it takes to go around is at the denominator, and here that will be the distance around the circle. And then you plug it in. So 115 equals, so 2 pi r over 60 over 1. Do that with your computation because I've seen people making mistake at that point. When you divide by 2 pi, you have to be careful to prime the denominator. So it's divided by 2 pi. And you get that? I do it with my calculator so you can see that if you don't put a parenthesis here, then it will divide by 2 and then multiply by pi, which you don't want. So it's very important that when you divide, you prime the denominator. If you don't do that, you're going to do a mistake, and you can, I guarantee that in the multiple choices, they know the mistake that students do. Is that clear? Mm-hmm. Okay. So the answer is C. Did you all say C? E. E. You're right. Thank you. What's your name? Taya. Taya. Yes. Yes. C. E. 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 Agree? Mm-hmm. Okay. Okay. So now do it on your own. Remember the proportions. 1 revolution is 2 pi r, is 360, is 2 pi. Okay, so remember, 2 pi is a way to measure angles, and it's going to be in radians, which is the same thing as 360, which is the same thing as 1 revolution, which is the same thing as in distance 2 pi r. That will be in meters. This is in degrees. This is in radians. And remember that speed, okay, speed is a scalar, is the distance, so the total distance that you can measure with a string, okay, or measuring tape. And here you have the time, and you put a leg here. And the unit here is in meters, and here is in second, and the unit here is meter per second. Okay? Are you doing it? Cute. So 1 revolution, you see it's not hard, right? 1 revolution is 2 pi r, and r is given to you. So if you have 830 revolution, it's gonna be cross multiply, right? So it's gonna be 8 times 2 pi r. That's in distance. So here we have distance in meters, and that's revolution. You done? Thank you. Good job. Yes. Yes.
What is it? 830.
Uh, yeah. Yeah. Thank you. That was your question? Yes. Okay. So the speed is gonna be 830 times 2 pi times 0.29, and it says in 1 minute. So 830 revolutions per minute, and 1 minute is 60. So do it.
Minutes, minutes, seconds.
So yes, you have to convert a minute to seconds, because usually the speed is in meter per second.
So at the end we convert it.
You can convert at the end. You can do meter per minute and then convert to per second. Is that clear? So what do you get?
25 point.
25.2?
Yeah.
Okay? Yes? So 2 pi, look back at your polar graph. Where are you going? Where are you going home now? So 25. You know what I'm going to do? I'm going to put the attendance. I should do that, right? Maybe I'll do it. Okay, so remember, acceleration is a force, right? So a force per unit mass. Okay, so what else here? So if there is a force, the centripetal force, that means you have an acceleration. So it's counterintuitive because it's not like the acceleration we were working with. Okay, this is a special kind of acceleration. It just means that the force is pulling toward the center. Okay, so this is called a centripetal force. Then, if there is a force, there is an acceleration. The acceleration is, in magnitude, the speed squared over the radius. So, for example, the way you can understand that, one way you can think about it is, and that's how Newton came up with the universal gravitation, right? So if you have the Earth, the question is why is it, if you remember the movie that you had to watch at the beginning, why is that? Newton asked, how come the moon does not fall on the Earth, right? When the apple does fall on the Earth, why is it that the moon doesn't fall toward the Earth? And the answer is it does, right? So what's happening here? The moon wants to keep going straight and at a constant speed. No, it can't. So actually, it's falling, right? And it does have an acceleration. It's accelerating toward the Earth, but it never reaches the Earth because the Earth is curving away. Okay, so I want to go in straight and at a constant speed. No, you can't. You have to fall, right? You have to fall toward the Earth, right? And why? Why is that? Because there is a there is a centripetal force. And if there is a force, it's a vector. If there is a force, that means there is an acceleration. So you don't want to think acceleration is slowing down or speeding up. Acceleration is a force per unit mass. If there is a force, then there is an acceleration. That acceleration is called the centripetal force. So V squared over R. Okay, so the magnitude of the acceleration is the speed squared over the radius. Okay, so it depends on the speed and on the radius. So for example, if you're on the highway and you're making a turn, what is it the first thing you want to do? Do you speed up or you slow down? Slow down. If you don't, off tangent you go. Is it harder to make a turn, a sharp turn, or like a long turn? Sharp turn, right? It's harder. So that's why the force that you need is inversely proportional to the radius. That means sharper turn, more force you need. And also it depends on the speed. But this is a killer here. Is it the speed or is it the speed square? Square. What does that mean? It means that if you multiply the speed by 2, the force that you need to make the turn is multiplied by 4. If you multiply the speed by 3, the force that you need to stay on track will be multiplied by 9. Okay? So you have to be very careful. If you go from 30 miles per hour to 90 miles per hour, first of all, you get a ticket. But plus, you need 9 times the force. And the force that keeps you on track is friction. If there is not enough friction, off tangent you go. Okay? So this is the life saving. Slow down. When you make a turn, you have to slow down. Otherwise, off tangent you go. Circular. So you see, each time you make a turn, you need a force to push you toward the center. Otherwise, off tangent you go. Faster you go, more force you need. Okay? Is that clear? Thank you. So what do you think of this question? Thank you. Yeah. See? Yes, yes, yes. Thank you, thank you. What's your name? Gabby. Yes. Right? Um, when you make a turn, like you're the pilots here with the airplane, can they turn like this or do they have to do that? Yeah, they have to do that, right? Why is that? So remember, as I told you, that forces are vectors and they come in with components, right? And each component has a different job. So for example, here, so first of all, you push on the air. So the air is pushing back on you, right? So you have the force here, which is called the lift. So this is the lift, right? But it has two components. One component, you go from the tail to the head. So it has a X component and a Y component. So the X component here is toward the center, right? So that will be your X component. And the Y component here is actually making the lift happen, right? So you push on the air push back, so you can stay mid-air. But you have also this component which is pushing the airplane toward the center. So that component, thank you, is called the centripetal force, right? So if you want something to stay on track, you need to provide the force toward the center, right? So you know that if you run and you're making a turn, you have to pull with one leg, right, to push you inward. That's how centrifuge work. So, for example, most of you are in biology, right? You have worked with a centrifuge. So, in the blood, you have the plasma, you have the red cell, and whatever, plaquettes, something like this. Yeah. Platelets, it's called plasma, red cell, and what? Something else, huh? Plaquettes, the plaquettes, something. Oh, anyway, you have three components. So it's gonna spin, right? All the components need a centripetal force, right, to stay toward the center. But this one, the heavy stuff, will have more resistance, right? Because it has more inertia, right? So it will move farther away. If you want to think about it, you can say it wants to keep going in a straight line at a constant speed. No, it can't. There will be a force here pushing toward the center from the liquid, but it will be more efficient with the lighter stuff than for the heavier stuff. Does it make sense? So if you are using a dryer machine, the heavy stuff will be outside and the soaks and the little stuff will stay inside. So that's the idea of a centrifuge, and that works on the same principle. Okay, let's do some computation. It's still an acceleration. Centripetal acceleration is still an acceleration. And you can comprehend, what's the effect on the human body if you divide by g. So you can compute an acceleration in g. So for example, you have those rides, amusement park, an amusement car park, and they will say, oh, you're going to experience 2g. What does that mean? It means you're going to feel twice your weight crushing you. You're going to experience 3g. That will be 3 times your weight crushing you. So, for example, if you are in a car, right, and you speed up very quickly, you're going to be pushed backward. Does that make sense?
Mhm.
And if you do it very aggressively, okay, so the acceleration is huge, right? If you accelerate with 2g, everything happens. You have twice your weight pushing you. You cannot go over 10g. If you go over 10g, you're gonna pass out and pass away. That's because if you have too much weight pushing you, the blood cannot get to your brain, right? And then you pass out, and too much, that's it, right? And also the blood doesn't get to your eyes, so you see dark. Everything goes dark, and other stuff as well. So you can measure, you can understand the acceleration by dividing by g. So for example, now I'm supporting my own weight. So the acceleration is 1g. If I go in a space shuttle, at the time when we had the space shuttle, it was 3g. So that means when you land off, you will feel 3 times your weight. Okay, so when you take off in an airplane, you're going to be pushed back, right? So anyway, let's do that problem and let's compute the acceleration in g's. So do it, okay? Don't you just plug it in. You just plug it in. Okay, so plugging in, the acceleration is the speed square over the radius. You can feel here that when you're going to make that turn, okay, you're going to feel pushed outward. And if the acceleration is, the curve is very bad, you're going to be pushed even harder. Your stomach is going to be very sick. You're going to throw up if it lasts too long. Depends how sensitive is your stomach. You know, your stomach is like an acceleration sensor. It depends on people. That's why you are. Some people are sick in cars. Car sick. Okay, so don't wait for me. Okay, so the first turn, your speed is 34 meters per second, and the radius is 33. So the acceleration in that case, okay, so it means here, you want to keep going in a straight line at a constant speed? No, you can't. Oh, it's gonna hurt. You're gonna be pushed this way. But your body wants to go outward, right? You're gonna be pushed out. That's what you're gonna feel in your guts. You're gonna be pushed out. So the snow here is gonna push you in. That's called the centripetal force. But in your guts, you're gonna be pushed out. So how much is that? 34 square divided by 33. It's gonna be 35. But it's very hard to understand what does 35 meters per second means. So that's why we're going to divide by g, by 9.8, by 10. So let's see. G is about 10 meters per second square. So the acceleration is going to be
3.5.
Thank you. 3.5 g. What does that mean? It means you're going to feel 3.5 times your own weight pushing you, right? You don't want that to last too long because the blood, has a hard time to get to your brain and you can pass out. So you don't want that to last too long. Okay, and you have to be trained, otherwise you fall up, and it's very hard on the body. Is that clear?
Yeah.
So 3.5 G means 3.5 your own weight. Okay, so 100 pounds, that will be times 3, so more than 3 pounds pushing you. Let's do this one. It's going to get worse, right? Because the curve is smaller. It's smaller radius, right? So let's do that. Centripetal acceleration is the speed divided by the radius. So the speed is the same, but now the radius is 24. Which is
48.7.
so 48.
0.17.
Okay. So if you divide by 10, so about 5G. Oh, that's very bad. So that will mean 4 times your own weight crushing you, pushing you. Everyone, any questions? Okay, so if you are looking at this from outside, what you're gonna see? You see that because of inertia, okay, this here wants to keep going in a straight line at a constant speed. No, it can't. It's gonna be pushed in, right, by the wall here, right? So that's called a centripetal force. The centripetal force that you're gonna need to provide, but we're gonna see that next, equals mv squared over r. But don't worry about that. So that's what you see. But now you are in the frame of reference, you are inside here. What you're gonna feel? If you are inside here, that's your frame of reference, you go zoom. What you're gonna feel in your guts? What you're gonna feel on your body? Push out, right? Like on your like if you go on a merry-go-round, you're gonna be pushed back. So in your frame of reference, that's not called a centripetal force, you're going to call it a centrifugal force. So sometimes you have conceptual questions, and sometimes it's easier, right, if you think centrifugal and not centripetal. So it's a matter of frame of reference. Is that clear? So for example here, that's the way they train astronauts, right? So they put them. I don't think they tied them. That's just a cartoon. But you can see that if you spin the wheel very fast, okay, all his bones are gonna be crushed, right? And he's gonna die. So if you make it fast enough, if you go over 10G, right, then he dies. So he says you're going to experience a centripetal force because your body wants to keep going in a straight line at a constant speed, knowing you can't, right? It's going to be pushed in, crush the bones. But he says, okay, but in my frame of reference, I'm going to experience a centrifugal force, right? Because he feels that he's being pushed out. And he replies, it doesn't matter, right? You're going to die anyway. So at the end, the frame of reference does not matter because at the end, the consequence will be the same. Okay? So I have like a small demo. And you understand this demo only if you think centrifugal force, right? Thank you. Yeah. Did you put your name?
Yeah. You have to put the name the
Recycle.
second.
Recycle for the trees and the planets. Give me just your okay. So this is water. give me your best? Yeah. Okay, so imagine in the frame of reference of the water, yes, right? If I take that water upside down, what's gonna happen? Let's go. Because of gravity. But if I spin it, the water is gonna feel two forces, right? Gravity pulling in, but also the centrifugal force. And the goal is to make the centrifugal force larger than the force of gravity. Agree? Yeah. I cannot change the radius, but I can change the speed, right? So let's see. I'm gonna aim at you. Does it work? Oh, wow. And there is no glue. So imagine you want like a few points extra. You can do it. The best way to do it is with a bucket. You take a bucket full of water and 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 you do this, and it should work. But don't practice at home. So we can go up to 10G. Since you are in biology, you can look it up. The effect of too many G's. The only thing I remember is that the blood doesn't get to the brain, so you pass out and you see all dark, blackout, right? But of course, too many G's, you can crush your bones and it will be terrible. Okay, so someone sent me, I think last semester, like a video, and she's a pilot. Did I show you this one? So he's gonna spin, and you see the water from, this is red bird. Do you see that he is spinning? He's spinning. You see? You see the landscape now is there? And the water doesn't spin. Isn't that crazy? So, from the point of view of the liquid, that will be the centrifugal force pushing. And I don't know what he's doing. He's spinning in the other direction. This is not healthy, what he's drinking. Okay, and you can see this. This is a pilot, and she's gonna pass out.
Let's get after it.
7G.
Squeeze those legs. There you go. We're off the G.
Boom. She passed out. And then she comes back.
Hey, Emily, you back with me?
Yeah, but I think I might pass out.
So 7G, that will mean 7 times your weight, crushing you, right? A lot of pressure. So the blood doesn't get to the brain, thank you. And other stuff as well, which I forgot. Okay, so try to do this one. We are back to math. If you have any question, let me know, okay? If you have question, other people might have the same question. So you identify the physical quantity. Here it says meter per second, so that means that's going to be the speed. And here you look at the unit, it says 4 meter per second per second. So that means that's going to be very good, an acceleration. Thank you, thank you. So what is the radius? That will be R and question mark. Thank you, thank you. Okay, so the equation, centripetal acceleration equals v squared. Thank you, thank you. That will be speed square exactly over the radius, and then you go over 1 so it doesn't fall. And then you plug it in, right? So do it, don't stare. 4 equals 15 squared over the radius. So it's like solving a proportion. You cross, multiply, divide, get R. Thank you, thank you. $15 squared over 4. So what do you get? 56. Yes, 56 meters. Is that clear? Yeah. So that's the whole story. If you want to keep on the track when you are making a turn, right? You want to make sure to slow down, because what is the force that keeps you on the track? That will be friction. It's the friction, the static friction. So if there is not enough friction, if you didn't rotate your tires like you're supposed to, if it's icy, or if you are doing aquaplaning, off tangent you go and boom, insurance goes up. Okay, so sometimes it depends on the equations, but sometimes it's more convenient to use this equation instead. So it's a little bit of algebra. You see, v squared over r. You substitute v by 2 pi r over t. Okay, you plug that into here and you get that equation here. So sometimes it's easier to use this one. You don't have to. You can go step by step, but if you can go faster, you can use this. Okay? So let's do this one quickly. You can use that equation instead. It's just to review scientific notation. Right? And it's good even for chemistry. It's good to review scientific notation. It doesn't hurt. So you can use that equation instead. Are you doing it? Okay, you just plug it in. So that's the distance between the Earth and the Sun. This is called the astronomical unit. Okay, it's like 93 million miles between the Sun and the Earth. That will be in meters. So 1.5 times 10 to the 11. And now the big questions. Let's see if you listen. How long does it take the Earth to go around the Sun? Huh? What? 4.5. Yeah. So 360? 365? Yes? So 365 days. No. Put it into segments. No. I have a different way to do it. Why am I doing it this way? Let's put that in seconds. Do you remember what I told you a long time ago? 1 year is, yes, 3.15 times 10 to the 7 seconds. Do you remember that? 1 year is about pi times 10 to the 7. It can save you time. 1 year is about pi times 10 to the 7 seconds. Otherwise, you have to do 365 times 24 times 3600. This is a shortcut. Do you agree? 1 year is about pi times 10 to the 7. It can save you time. So you do 4 pi square. Okay. 1.5 times 10 to the 11. So we review scientific notation. Divide by, open the parenthesis, 3.15 times 10 to the 7, close the parenthesis. Oh, I messed up. Do you see where I messed up? In the equation, there is a square. It's a square here. You need to put a square. Okay, there is a square here. So you have to take the time and then you have to square it. Yes. I don't know why I'm becoming deaf. What do you say? What's supposed to be a 4?
Yeah.
This is a 4. You don't like my 4? Yeah, it's a 4. It's 4, 4, 4. It's a 4. So what you get? 4 pi square times 1.5 times 10 to the 11 divided by 3.15 times 10 to the 7. You square it. Don't stare. Do it. More you do in class, less you do at home. This one?
Yeah.
So A, you're right, right? So 1, 2, 3, 5.9 times 10 to the negative 3. Yes, everyone?
Yeah.
So it's good to review scientific notation. Okay, let's do you want to practice a little bit? Let's see let's do number 1. Remember, in Dropbox, you have tutorials now that I put at the root, right? Tutorials. One is about trig. So you need to review trig, cosine, sine, tangent. And one is about vectors, because we're going to work with vectors a lot. And remember, I'm not here on Thursday. So that's why you have homework, so you don't get bored. Right? So Thursday, there is no class on Thursday. So acceleration is v squared over r, right? So you just plug it in. And what do you get? Right? 5.6 meter per second. So it's not even 1g. You're going to be pushed out, but that's not that bad. Okay, let's do number 2. So you see, you identify, so this is R, and then here, look at the unit, meter per second. So that means it's an acceleration. How fast? That means you want to find the speed, okay, the magnitude of the velocity. Okay, so that's just algebra. So v squared equals 22 times 0.25. So you take the square root, right? And you get 2.35. Exactly. For something to stay on a circular path, you need to provide a force that will push toward the center. Okay, so this is called a centripetal force. Okay, let's see. Okay, let's do number 4. So this one is easy. So you have the radius and you have the speed. You want to find the acceleration. So that's gonna be 16, very good. So it will be 1.6 g. So 1.6 times your own weight pushing you, because you're going to be pushed against the if you are the passenger, you're going to be pushed toward the door, right? And if you don't have a seat belt and the window is open, off the window you go, right? It happened. So that's why you have to wear a seat belt. So this one is easy. Number 5, you can do it in your head. So you just look at the unit. So this is your acceleration, this is your speed, and you put radius question mark, right? So AC equals V squared over R. So 9 equals 3 squared over R. So R equals, that's easy, right? R equals 1, very good, meters. Okay? Okay, the other thing I want to bring your attention to, very useful also in science, is that you see when you have centripetal acceleration, okay, equals V squared over R. What does that mean? It means that, you see, it's inversely proportional to the radius, but it's proportional to the speed squared. Typical conceptual question. What does that mean? It means if the radius is multiplied by 2, so it's not sharp, right? It's a gentle curve. Thank you. If the radius is multiplied by 2, what's going to happen to the centripetal acceleration? Because it's at the denominator. If the radius is multiplied by 2, inversely proportional, that means the acceleration will be divided by 2. Typical conceptual question, right? If, thank you. If the radius is multiplied by 3, the centripetal acceleration will be divided by 3. This is called the inverse relationship. It's like y equals 1 over x. If the radius is divided by 2, what's going to happen? The centripetal acceleration is going to be multiplied by 2. But you see, it's proportional to the speed square. So if the speed is multiplied by 3, the acceleration will be multiplied by square 9. Okay, typical MCAT question, for example, or GRE. If V is multiplied by 2, acceleration is multiplied by 4. If V is multiplied by 5, acceleration is multiplied by 25. Proportional to the speed square, inversely proportional to the radius. Okay? So what does that mean? It means you go 60 miles per hour, and then now you go 30 miles per hour. So let's say you do the opposite. You go from 30 miles per hour to 60 miles per hour. So the speed is multiplied by 2. So that means the acceleration will be multiplied by 4. Very good. So it means you need 4 times the force. So 4 times the friction. So if there is not enough friction, if it's icy, okay, or if there is a hurricane, aquaplaning, off tangent you go. Okay, so let's so for example, if this is a velocity here, we already know that, right? What is the answer? What's going to happen here? If you cut the string here, right? If there is not enough force, will it be on the track or off tangent it goes? Off tangent, right? Because it wants to keep going straight and at a constant speed, so you need a force to pull it in. Otherwise, off tangent it goes. So talk to each other, try to answer this, and do it. More you do here, less easier it will be for test number 2, right? Typical question on test number 2. So you have a centripetal acceleration. What's going to happen if the speed is double? So double means multiplied by 2. So what's going to happen to the acceleration? Multiplied by 4. Do you all agree?
Yeah.
Okay, acceleration is proportional to the speed square, inversely proportional to the radius. Inversely means if you multiply the radius by 2, acceleration will be divided by 2. So what about the velocity? And oh yeah, what about the velocity? You can go back to the slides. You have a test today that everyone is tired. What's happening to the velocity relative to the path? So it's the acceleration is perpendicular to the path, but how do we call that? The velocity is tangent. Okay, it's like kissing the path here. So it's tangent. This is called tangent. Okay, so in a uniform circular motion, the velocity is tangent. Tangent to the circle, C. Oh, look, we are done. Yay! Boom. Any questions so far? So for the assignments, do remember the first trial, you don't want to look at the solution, right? You want to try very hard. You can work in a study group. You can help each other, talk to each other, and you can look at the solution or at least look at the hints only for the second trial, right? And if you do that, plus you do the review exam, it's not that hard. And the grades were good, right? Most of you did have good grades. So anyway, let's talk about force now. Okay, so a force is a push or a pull. So for example, if I have a spring scale, so I have a spring scale here, right? You can see the spring scale. I can attach like a weight, right? So now it's gonna reach an equilibrium. What is pulling down?
Gravity.
Gravity. And what is pulling up?
The spring.
The spring. It's called the tension. And you can measure the force here. Here, the force here, it says 2.25 Newton. So the way for measuring force is the Newton or the pound in the British system. But usually we use Newton. So this is called a spring scale. So the thing to understand is that if there is a force applied, there will be an acceleration. It could mean three things: speeding up, slowing down, turning. Or you can turn and speed up or turn or slow down. Okay? So you need a force only to change the state of motion, to go faster, to go slower, or to make a turn. You don't need a force to keep moving. If you have ice, for example, like ice ring, and you push something on it, it will keep moving forever because there is no friction. Okay, so the Newton is the unit for force. It's named after Newton, obviously. And it means kilogram. And what is meter per second per second?
Acceleration.
Acceleration. So what's the equation? Force equals mass times acceleration. Force is a vector, acceleration is a vector. Acceleration just means force per unit mass. Okay? So pound is, we are the only country with another South America country, which I forgot, to use pound. All the other countries gave up on pound, and they don't use pound, except us, right? So 10 Newton is about 2 pounds. So it's a unit of force. It's not a unit of mass. A kilogram is a mass. But pound is a force. It's to measure force, right? So you have two kinds of forces. You can have contact force, so that means you have to touch, right? So for example, the pull here, you kick here, there's a spring and you're pulling the spring. Or you have also forces at a distance. So gravity does not need to touch you, right, to pull you back toward Earth. So that's a force at a distance. Electrostatic force is a force at a distance. Magnetic force is a force at a distance. Okay, so a force is a vector. Okay, so it has a magnitude, a unit, and a direction. So remember, you can take this vector, you can cut and paste here, you can cut and paste there, and these are all the same vectors. Do you agree? Mm-hmm. Not that. So just a review here. Let's take a vector. Cut, paste a vector here. I can cut and paste anywhere I want. It's going to be the same vector. Okay, so I take that vector, I can move it around. Here, there, it's always the same vector. So each time you have a vector, first thing you want to do is to attach the tail to the origin. So I'm going to move the origin here. If I can do that here, right? So that point here is going to be the head of the vector. Okay, so the x component will be 8. Okay, you go from the tail to the head. So you're going to run, and then you're going to rise. or you can rise and then run. So that will be the X component, that's going to be 8, and 6 here will be the Y component. You remember that? You can use also standard notation. That will be the magnitude, and this is the angle, always relative to the positive x-axis. So if you go counterclockwise, it's going to be positive. If you go clockwise, it's going to be negative. If you use that notation, the x component is always cosine and the y component is always sine. In Dropbox, you have tutorials to go over again vectors, component of vectors, and trigonometry. And especially because I'm not here on Thursday, then you can review. Okay, so vectors come in two components. Each component have a different job. For example, when you are lifting a weight, here you have two components. Here, X component that will bring the weight towards you, and Y component that will lift up. So it's not because you are delivering 8 pounds that here you can lift 8 pounds. Okay, it depends on the component. Is that clear? We already talked about that. What's going to happen in this case here? You see, you have force. That will be the application point. So this is a horse, and you have a force here. What's going to happen to the bolt? It's going to be pushed on the side, right? Because that force has two components. One component is making the boat moving forward, so it has an acceleration, x along the x, but this component is pushing on the side, which is not good, right? So what do you need? Usually, you need you are very tired today. What do you need to make it move? The boat is going to be pushed on the side. So you need another horse on the other side. Does it make sense? So for example, here you have like, I don't know if you know that. I don't even know how it's called. Like if you have enough momentum, you can go up the wall, right? I think it's called wall walk or something like this, right? That can happen. That can happen because there is a force on the wall, right? So what's happening here? So we're going to see that Newton laws, for every action, you have a reaction. So if you push on the wall, what's going to happen? The wall is going to push back, right? So you push on the wall is going to push back on you. That force here has two components. Can you trace the components on your notebook or tablet? You see that vector here? That's the vector force on the wall. Can you stop staring and trace the components of this vector here? You go from the tail to the head. Can you trace the components? Tail to head. You remember you have tutorials in the Dropbox, right? How to find components of forces, because I'm not going to be here on Thursday, so you can catch up. It has two components. That will be, you can think of that as the X component, yes? And that will be the Y component. Where does that force comes from? That force is pushing you up. What is that coming from? Yes, but what is that? When I do that. The friction, static friction. Static friction is pushing you up. Here, that force here, we're going to see it's called the normal force. It means if you push something, it's going to push back on you. Okay, it's like a support force, push back on you. So from the wall, you're gonna have a force. This force has two components. The normal force that's gonna stop you, stop your momentum, and this force that will turn that momentum that you had into a vertical momentum. Okay? So my point is that components have different jobs. That's why it's very important that you open your Dropbox and you go over the tutorial about trigonometry, how to find components of forces, right? Because I feel that not everyone has digested the thing. So make sure you do it, otherwise it's going to be painful. I wanted to show you something here. A goat knows physics, right? Did you see? It has the momentum to begin with, right? So it has a horizontal momentum, and then vertical momentum. So if you can do that, I will give you extra credits. It's a thing, okay? People do that. Okay? The pop quiz is very easy. So we still have time here. You see, you have a pole. So this is a force. This is the tail. This is the head. This is the magnitude. And that will be the angle, okay, from the positive x-axis. Can you find the components? So this one is easy, right? Can you find the components? And I'm going to lose everyone because everyone is on the pop quiz. I messed up. The pop quiz was open